A clock ticks. 1 second passes, then another, and another. Time marches forward with relentless certainty, the same for everyone, everywhere. Or so we have always believed. But what if time is not the universal constant humanity imagined? What if it can slow, bend, even freeze not metaphorically, but as fundamental physics? At the edge of a black hole, time does something physics textbooks said was impossible. As an object approaches the event horizon, the boundary beyond which nothing, not even light, can escape, the clocks carried by that object appear to an outside observer to tick more and more slowly. Minutes become hours, hours become centuries, and at the horizon itself, time appears to stop altogether, completely, forever. This is not magic, it is not illusion. It is the direct prediction of Einstein's theory of general relativity, confirmed by decades of experimental evidence. Time, the invisible fabric that threads through every moment of human existence, can literally freeze. Yet the question becomes more disturbing when probed deeper. If time can stop, does it truly exist as something fundamental? Or is time itself like space, like distance, an emergent phenomenon arising from something more basic? The human brain, that biological marvel that perceives duration and change, experiences time as absolute. A second feels like a second. The past feels irretrievably gone. The future feels unreached. Yet neuroscience reveals that even subjective time is constructed, malleable, dependent on attention and emotion, and the firing of neurons in distant brain regions. At the smallest scales of reality, in the quantum foam, where particles flicker in and out of existence, time may not even exist. It may be created, assembled, emergent. At the largest scales, near cosmic horizons, and in the depths of gravitational wells, time warps and bends beyond recognition. This is the paradox of time. It seems more fundamental than anything, yet evidence suggests it is less fundamental than everything. This is the mystery that physicists, philosophers, and neuroscientists continue to unravel. Can time truly stop? The answer is both more profound and more unsettling than the question suggests. For thousands of years, humanity understood time as something simple, obvious, unchanging. Time flowed like a river, the same for all observers, the same everywhere. The ancient philosophers pondered its nature, whether it even existed, whether it was cyclic or linear, but none questioned its universality. In the 17th century, Isaac Newton crystallized this understanding into mathematical laws. Time was absolute, Newton declared. It was the constant backdrop against which the universe unfolded. Space was absolute too, a fixed, unchanging container. Matter moved through this absolute space in response to forces, measured against the constant ticking of absolute time. The entire Newtonian cosmos was like a vast clockwork mechanism, perfectly deterministic, perfectly predictable, with time serving as the universal metronome, keeping all things synchronized. This view held sway for centuries. It seemed intuitive, obvious, grounded in everyday experience. A second on Earth was a second on Mars, was a second at the edge of the universe. One person's moment of time corresponded exactly to the same moment elsewhere, despite the separation. Causality flowed forward along a river of time that all observers floated upon together. The mathematical machinery built upon this foundation was extraordinarily successful. Using Newton's laws and his conception of absolute time, scientists predicted planetary motions with stunning accuracy, calculated the trajectories of comets, explained the tides, sent spacecraft to distant worlds. The success seemed to validate the entire edifice. Time is absolute, universal, fundamental. Yet beneath this success lurked puzzles that even Newton's framework could not resolve. Light, those ancient physicists discovered, traveled at a constant speed. But constant relative to what? Relative to the medium through which it propagated. In sound waves, the speed of sound is different depending on whether the observer moves toward or away from the source. Should light not behave similarly? By the 19th century, physicists had developed a theory of light as a wave propagating through an invisible medium called the ether. The ether was imagined to fill all space, providing the substrate through which light waves rippled outward. But experiments searching for evidence of the ether kept failing. In 1887, physicists Michelson and Morley performed a precision experiment that should have detected the ether, but found nothing. The null result was puzzling, disturbing, a violation of expectations rooted in what seemed like common sense. The puzzle remained unsolved until 1905, when a young patent office clerk in Bern, Switzerland, published 4 papers that would transform human understanding of reality. Albert Einstein began with a simple but radical assumption. The speed of light is constant for all observers, regardless of their motion. Not constant relative to some medium, but constant absolutely. This assumption led to consequences that seemed to violate everything intuition suggested. If the speed of light is constant for all observers, then time cannot be absolute. 2 observers in motion relative to each other must measure time differently. For the faster observer, time passes more slowly than for the stationary observer. A clock moving at high speed ticks more slowly, not because something is wrong with the clock, but because time itself flows more slowly for the moving observer. This is time dilation, the first hint that time is not the simple, universal phenomenon Newton imagined. The effect is tiny at everyday speeds but becomes dramatic as velocities approach that of light. Particles created in the upper atmosphere by cosmic rays and moving at 99.9% of light speed have lifetimes in their own reference frames, much shorter than in Earth's reference frame. This time dilation has been measured countless times. With sophisticated equipment, muons decay more slowly when moving at relativistic speeds. Satellites' clocks tick slightly faster than Earth clocks due to their motion. Time, Einstein showed, is not independent of space. They are woven together into a single continuum. Space-time. The passage of time is relative to the observer. It depends on motion. It depends on acceleration. Most profoundly, it depends on gravity. In 1915, Einstein published his general theory of relativity, extending special relativity to include gravity, and here the relationship between time and gravity became explicit and undeniable. Gravity is not a force pulling objects downward, Einstein proposed. Gravity is the geometry of space-time itself. Massive objects warp the space-time around them, curving it, bending it. Objects do not fall because they are pulled. They fall because they follow the curved geometry, the geodesics, the straightest possible paths through warped space-time. But this warping affects time as well as space. In regions of strong gravity, time moves more slowly. This is gravitational time dilation, and it is as real and measurable as velocity-induced time dilation. Consider Earth and the Moon. Earth has more mass, hence a stronger gravitational field. At Earth's surface, time passes more slowly than it does on the Moon or in space far from any massive body. The effect is tiny. Someone living at sea level ages very slightly more slowly than someone living atop a tall mountain, but it is real. Atomic clocks, the most precise timekeeping devices humans have created, demonstrate this effect. A clock 1 meter above the ground ticks faster than an identical clock on the ground. The difference is only nanoseconds per day, but it is measurable. For extremely massive objects like neutron stars or black holes, the effect becomes extreme. Near a neutron star, time dilation becomes pronounced, and near a black hole's event horizon, time dilation approaches infinity. This realization forced physicists to fundamentally reconsider the nature of time. Time is not universal. It is not absolute. It flows at different rates depending on where you are in the gravitational field. Time is woven into the fabric of space-time, dependent on gravity, relative to the observer's position and motion. Yet Einstein's success also revealed new mysteries. His equations seemed to break down at certain points the singularities, where density and curvature became infinite. Inside black holes, his equations suggested that time itself might behave strangely, perhaps even cease to exist as something meaningful. Moreover, Einstein's classical theory of gravity provided no clear understanding of what time fundamentally is. It described how time behaves near massive objects, but it did not explain time's origin or its ultimate nature. It showed that time can be dilated, bent, slowed, but it left open the possibility that time itself might be emergent, derivative, not fundamental. These questions would require an entirely new framework, quantum gravity, where the classical smoothness of space-time would encounter the probability and uncertainty of the quantum world. And there, in that collision of two great theories, the very concept of time would face its deepest challenge. Nowhere in the observable universe does gravity reach more extreme manifestations than at the event horizon of a black hole. Here, space-time curvature becomes so profound that the equations describing it break down, and time, that seemingly fundamental aspect of existence, enters a regime where its behavior becomes almost incomprehensible. The story begins with a question: what happens when a star dies? Some stars, at the end of their lives, exhaust their nuclear fuel and collapse under their own gravity. If the star is massive enough, at least 20 times the mass of Earth's sun, the collapse becomes unstoppable. The material crushes inward, compressing to ever higher densities until, according to Einstein's equations, the entire mass concentrates at a single point, a singularity. Around this singularity lies a boundary, a spherical surface called the event horizon, defined by a critical distance known as the Schwarzschild radius. Within this radius, the escape velocity exceeds the speed of light. Because nothing can travel faster than light, nothing that crosses the event horizon can ever escape. Light itself, when emitted from inside the horizon, cannot reach an external observer. The region is black, but there is something far more profound than the trapping of light happening at the event horizon. There is the freezing of time. Consider an observer far from a black hole, watching from a safe distance as another observer falls toward the black hole. To the distant observer, something miraculous appears to happen. As the falling observer approaches the event horizon, their clocks appear to tick more and more slowly. Minutes on the falling observer's watch correspond to hours, days, years, as perceived by the distant observer. This is gravitational time dilation, taken to an extreme. The gravitational field of the black hole is so intense that it creates a dramatic differential in the flow of time. According to the Schwarzschild metric, the mathematical description of space-time near a spherically symmetric black hole, the rate at which time flows depends on the radius r and the Schwarzschild radius r. S. As an object approaches the Schwarzschild radius, the time dilation factor approaches 0. At the event horizon itself, where r equals r, s, time dilation becomes infinite. From the perspective of the distant observer, the falling object appears to slow its approach to the event horizon asymptotically. It gets closer and closer, but never quite reaches the horizon. Within any finite time, the falling object appears frozen, suspended at the edge of the abyss, its clocks running slower and slower, eventually becoming imperceptible. This is not mere appearance. This is fundamental. The structure of space-time itself is such that, according to the distant observer's frame of reference, time quite literally comes to a stop at the event horizon. Yet here lies a profound paradox that perplexed physicists for decades. If nothing ever appears to cross the event horizon from the distant observer's perspective, how can black holes have grown and accumulated mass over billions of years? If time stops at the horizon, wouldn't material be frozen there eternally, unable to fall further inward? The resolution comes from recognizing that different observers experience time differently. From the perspective of the falling observer, the one approaching the event horizon, something entirely different occurs. Their own clocks tick normally from their point of view. They experience no sensation of slowing time as they approach the horizon. According to their experience of time, they cross the event horizon in finite, proper time, unaware of anything special happening until they are crushed by the singularity's tidal forces. This illustrates a central principle of relativity. What one observer considers now may not correspond to what another observer considers now. There is no universal present moment. There is no cosmic clock ticking at the same rate everywhere. Time is relative, personal, observer-dependent. But the black hole scenario raises even deeper questions. The singularity at the center is a point of infinite density and curvature, where Einstein's equations break down completely. Physicists have no reliable theory describing what happens at the singularity. Moreover, the very concept of time becomes questionable in such extreme circumstances. Stephen Hawking tackled this mystery from another angle in 1974, when he discovered something shocking. Black holes are not truly black. Due to quantum effects near the event horizon, they emit thermal radiation. This Hawking radiation is produced by quantum fluctuations in the vacuum virtual particle pairs briefly popping into existence and then annihilating. Sometimes one partner falls into the black hole while the other escapes. The escaping particle constitutes radiation that carries away energy from the black hole. Over eons, trillions of years for stellar mass black holes, this radiation causes the black hole to evaporate. The smaller it becomes, the hotter it grows, the faster it radiates, until finally it explodes in a burst of gamma rays. But this process raises a paradox about time and information. If material falls into a black hole and crosses the event horizon, and if an observer far away sees time freeze at the horizon, how can information about what fell in ever escape? According to the distant observer, the material is frozen at the horizon. Its information is trapped, inaccessible. Yet if the black hole evaporates through Hawking radiation, has that information truly been lost? Some physicists argued that it must be that black holes represent the only known process in physics where information is irreversibly destroyed, a violation of quantum mechanics' fundamental principles. Others argued that the information must escape somehow, encoded in subtle correlations in the Hawking radiation. The resolution, it appears, involves a deep connection between quantum entanglement, space-time structure, and the emergence of time itself, connections that remain only partially understood. These quantum mysteries point towards something profound. Time may not be a fundamental feature of reality, but rather an emergent phenomenon arising from more basic quantum information. Near black holes, where space-time becomes extreme and quantum effects crucial, time's emergent character becomes apparent. The black hole represents a limit point, a frontier, where classical space-time and quantum reality collide. Time slows to a stop at the event horizon from the external observer's perspective. Singularities mark places where time itself may cease to have meaning. The information paradox suggests that time and causality, the notion that effects follow causes, are intimately connected to quantum information preservation. All these clues suggest that time is not simply woven into the fabric of space-time as Einstein imagined. Rather, time may emerge from something deeper, from quantum correlations, from information structure, from the causal relationships between events. At black holes, where these quantum and gravitational effects become extreme, time's constructed, emergent nature becomes undeniable. At the scale of the universe, where stars and galaxies move through space at enormous velocities, time behaves in ways that challenge human intuition at every turn. The constant that makes everything possible, the speed of light, is also the speed at which time itself seems to approach a limit. When objects accelerate to velocities approaching that of light, they enter a realm of physics where time ceases to be a simple measure. Einstein's special theory of relativity describes this realm with mathematical precision, and experiments have confirmed its predictions thousands of times. Yet the phenomenon itself, that time passes differently for objects in motion, remains philosophically profound. Consider a thought experiment that physicists have contemplated since Einstein's era. Imagine a spaceship accelerating to a velocity very close to that of light, perhaps 99.9% of light speed. On Earth, observers watch the spaceship recede. From the spaceship's perspective, Earth recedes. But something peculiar happens to time. From Earth's perspective, clocks on the spaceship tick more slowly. A year aboard the spaceship corresponds to multiple years on Earth. If the spaceship could somehow reach exactly the speed of light, which, it turns out, nothing with mass can ever do, because it would require infinite energy, then time on the spaceship would, from Earth's perspective, freeze completely. This is not appearance. This is the fundamental structure of space-time. Time is dilated for the moving observer. It is as real as any other physical effect. But consider the reverse perspective. From the spaceship's viewpoint, Earth is receding at high speed. so Earth's clocks should tick more slowly. And indeed they do, from the spaceship's perspective. Yet there is no contradiction. Relativity permits this apparent paradox because there is no universal time, no cosmic clock against which both perspectives can be compared. Each observer measures time relative to their own reference frame. The implications are profound. A spacecraft that could accelerate to near light speeds and travel to a distant star could, from the star's perspective, take thousands of years to arrive. But from the spacecraft's perspective, only a few years pass. The travelers would age slowly. When they return to Earth, centuries would have passed while only decades passed aboard the spacecraft. Time travel to the future is thus already possible, a consequence of Einstein's theory. Astronauts aboard the International Space Station age imperceptibly slower than people on Earth, not due to the ISS's motion alone, though motion does matter, but also due to gravitational time dilation from being farther from Earth's gravitational pull. Yet what makes this scenario even more conceptually challenging is recognizing that no observer experiences being frozen in time. The travelers on the spaceship feel time passing normally. A year aboard the ship feels like a year. They are unaware of any slowing. It is only the external observer who perceives their time as slowed. This relativity of simultaneity in time raises a fundamental question. Is there any objective reality to time, or is time purely a function of reference frame and observation? The light speed represents the ultimate boundary. Photons, particles of light, travel at light speed. According to special relativity, time dilation for an object moving at light speed becomes infinite. From the perspective of a photon, if such a perspective were valid, which it is not according to physics, zero time would pass between emission and absorption, no matter the distance traveled. A photon, emitted from a distant galaxy and traveling to Earth for billions of years, according to the mathematics of relativity, experiences this entire journey instantaneously, from its own admittedly non-existent perspective. Time has frozen for it. But this raises another mystery. If time can freeze for objects moving at light speed, what does this imply about time's fundamental nature? In recent decades, physicists exploring quantum gravity have proposed radical ideas. Perhaps time itself is emergent, arising from more fundamental quantum information, rather than being a basic ingredient of reality. Perhaps at light speed, or near black holes' event horizons, time approaches the limits of its emergence and begins to break down. The physicist Leonard Susskind proposed that quantum complexity, the difficulty of describing a quantum state, might provide a deeper measure of time than classical physics suggests. As a quantum system evolves, its complexity increases. Perhaps time's flow is literally the growth of quantum complexity. At light speed, or in timeless quantum states, complexity would freeze, and therefore time would freeze. Furthermore, investigations of black hole thermodynamics and quantum entanglement have revealed that space-time itself, and by extension time as part of space-time, may emerge from more fundamental structures. If this is true, then time doesn't simply slow down at light speeds or near horizons. Its very nature as an emergent phenomenon becomes apparent. The speed of light, rather than being a limiting factor within time, might be the interface between time and pretemporal reality. The fact that nothing with mass can reach light speed might not be mere kinematic limitation. It might reflect the boundary at which time itself ceases to be a valid concept. These are speculations at the frontier of physics, but they are grounded in rigorous mathematics and decades of experimental evidence. They point toward a picture of time fundamentally different from common sense. Time is not absolute, not universal, not fundamental. Time is relative, observer-dependent, emergent. At cosmic velocities approaching light speed, time slows toward freezing. At black hole horizons, time freezes from the distant observer's perspective. In quantum regimes approaching the Planck scale, time may not exist at all. All these clues converge on a conclusion that is both exciting and unsettling. Time, the most intimate aspect of conscious experience. The river on which all life flows may be constructed, temporary, derivative. Below the scale of atoms, In the quantum realm where particles exist in superposition and observation determines reality, the classical understanding of time becomes even more problematic. The very foundations of quantum mechanics suggest that time may not exist at the quantum level in any fundamental sense. The Schrödinger equation, the governing law of quantum mechanics, describes how quantum states evolve. Remarkably, this equation is time reversible. Run it backward, and it describes the system's past as accurately as it describes the future. Yet the universe has an arrow of time. Events move from past to future, not indiscriminately backward and forward. Entropy increases. Order becomes disorder. Entropy never spontaneously decreases in isolated systems. This asymmetry, the arrow of time that pervades everyday experience, is not obvious in the fundamental laws of quantum mechanics. The arrow of time appears to be an emergent phenomenon, arising from the complex behavior of systems with many particles, not from any fundamental asymmetry in the laws themselves. More profoundly, quantum mechanics introduces indeterminacy into the very notion of time. In the classical world, a particle has a definite position and velocity at any moment in time. Its trajectory can be calculated precisely. In quantum mechanics, particles have no definite position or velocity independent of measurement. They exist in superpositions of many possible states. When a measurement occurs, the superposition collapses, and the particle is found in one of the possible states. But the measurement process is fundamentally non-deterministic. The outcome is random, probabilistic. Prior to measurement, the particle didn't have a definite value for the measured property. Measurement creates that property. This raises a disturbing possibility. If reality itself is fundamentally uncertain and non-deterministic at the quantum level, and if measurement creates definite properties, what role does time play? Some physicists, like Carlo Rovelli, have argued that quantum mechanics reveals time to be fundamentally relational, a property that exists only in relation to other systems, not as an absolute background against which systems evolve. In this view, time is not a dimension woven through existence, but rather an emergent result of interactions between quantum systems. The Wheeler-DeWitt equation, which attempts to describe quantum gravity, the fusion of quantum mechanics, and Einstein's general relativity, seems to eliminate time entirely from the fundamental description. In this equation, which describes the quantum wave function of the entire universe, there is no explicit time variable. Time does not appear. This profound result suggests that at the most fundamental level, the level where space, time, gravity, and quantum mechanics merge, time does not exist as a basic feature of reality. Instead, time emerges as systems become complex and developed into the classical realm, where it appears as an absolute, unidirectional flow. The physicist Donald Page and others have explored what is sometimes called the problem of time. The fact that fundamental physics cannot accommodate a meaningful notion of time. Classical general relativity describes space-time as a fixed, four-dimensional geometric entity. Quantum mechanics describes systems evolving in time according to the Schrödinger equation. These two frameworks cannot be simply merged because they treat time fundamentally differently. When physicists attempt to quantize gravity and merge these frameworks, time causes immediate problems. The result is theories like loop quantum gravity, causal set theory, and others that suggest time must emerge from something more basic. At the Planck scale, the smallest scale of length and time that physics can meaningfully address, quantum fluctuations of space-time, becomes so violent that classical concepts like position and time become undefined. The physicist John Wheeler imagined that space-time itself becomes a seething quantum foam at these scales, with wormholes and virtual particles constantly popping in and out of existence. In this foam, the very notion of time becomes suspect. Events may not have a definite temporal order. Causality, the notion that causes precede effects, may become meaningless. And time itself may be just one way of organizing information about quantum events, not a fundamental property. Recent theoretical work, exploring holographic principles and quantum entanglement, has revealed that space-time and time as part of space-time may emerge from quantum information correlations. If this is true, then time doesn't simply behave strangely in the quantum realm. Time's very existence there is questionable. The celebrated physicist Richard Feynman, in his characteristic style, pointed out that the quantum universe is fundamentally mysterious, and that human intuitions about time developed through everyday experience likely fail at fundamental scales. These quantum puzzles are not mere philosophical curiosities. They have practical implications. In quantum computing, where systems maintain quantum superpositions of many states simultaneously, time's role becomes ambiguous. Complex quantum systems don't seem to require a well-defined classical time to describe their evolution. The implications are staggering. If time emerges only at larger scales, from quantum systems becoming classical through decoherence and measurement, then the fundamental universe, the absolute foundation of existence, may be timeless. Time may be the ghost in the machine, a useful approximation for large systems but not a fundamental reality. At the quantum scale, time may not truly exist. It may be constructed, it may be emergent, it may be an illusion born from complex quantum information becoming classical. The universe itself has a history. The Big Bang Theory, confirmed by decades of observations from radio telescopes, satellites, and ground-based observatories, tells us that our universe did not always exist. Roughly 13.8 billion years ago, all matter, energy, and space itself were concentrated in an infinitely hot and dense point called the initial singularity. But this raises a question that has troubled physicists and philosophers. If the universe began with a singularity, what existed before? And what does it even mean to ask what came before, when time itself may have begun with the Big Bang? In general relativity, the Big Bang singularity is not merely the beginning of matter and energy, but the beginning of space-time itself. It is the point at which the curvature of space-time becomes infinite, and the equations of general relativity break down. According to Einstein's theory, time itself begins at the Big Bang. This statement requires careful interpretation. It does not mean that time was running before the Big Bang and then started running. Rather, the very concept of before becomes meaningless. Time, as described by general relativity, is woven into the fabric of space-time. There is no space-time before the Big Bang, therefore no time before the Big Bang. The physicist Stephen Hawking explored this concept using imaginary time in his formulation of quantum cosmology. In this framework, time becomes imaginary near the Big Bang singularity, which has the mathematical effect of eliminating the singularity. Space-time, near the Big Bang, in this picture, is smooth and finite rather than singular. But this raises new mysteries. If time is emergent and begins with the Big Bang, what is the Big Bang an emergence from? If time did not exist before, how did the Big Bang transition from non-existence to existence? These questions are not merely philosophical. They are central to modern cosmology. The universe's initial conditions determine its entire future. Yet, the Big Bang singularity represents a breakdown of all known physics. It is where general relativity, quantum mechanics, and thermodynamics all cease to make predictions. The universe today appears to be expanding galaxies receding from each other, space itself stretching. Observations of distant supernovae have revealed that this expansion is accelerating, driven by something called dark energy. If the universe is expanding, extrapolating backward suggests it was denser and hotter in the past, which led to the Big Bang model. But the acceleration itself poses a puzzle about time. In the far future, as dark energy continues to dominate, the universe will expand indefinitely. Eventually, stars will burn out, atoms will decay, black holes will evaporate through Hawking radiation. The universe will become cold, thin, nearly empty, a state sometimes called heat death. In this infinitely distant future, time itself may lose meaning. With no change, no processes, no events, what does time measure? If the universe reaches a final state of maximum entropy and thermodynamic equilibrium, has time effectively stopped? Conversely, if time emerged from quantum information dynamics at the Big Bang, as some theories suggest, will time dissolve back into quantum timelessness as the universe dies? These questions lead physicists and cosmologists to contemplate the deepest possible scenarios. The universe may be cyclical, with big bangs succeeding big crunches in an eternal cycle. Time would begin and end in each cycle. The universe may be one of many in a multiverse, each with different physical laws and different relationships with time. Some quantum gravity approaches, like the proposal that time emerges from quantum entanglement growth, suggest that the arrow of time, the direction from past to future, is not fundamental, but emerges as quantum systems become increasingly entangled and then decohere into classical states. Roger Penrose has proposed a bold idea called conformal cyclic cosmology, suggesting that the universe is infinite in both the past and future, but that what we interpret as the Big Bang is actually the infinite future of a previous epoch. Time is not linear but cyclic, with the end of one cosmic era becoming the beginning of the next. These cosmological scenarios all hint at a profound truth. Time is not a permanent feature of the universe. Time begins and may end. Time's direction is not fundamental but emergent. The cosmic arrow of time, the fact that time seems to flow in one direction, may be a consequence of the universe's special initial conditions and increasing entropy. If the universe is ultimately finite in time with both a beginning and an end, then time is temporary. Time is an accident of the particular quantum state in which our universe found itself at the Big Bang. In other universes, in other initial conditions, time might flow differently or not exist at all. This perspective dramatically alters the status of time. Time is not eternal, not necessary, not fundamental. Time is contingent. It depends on the universe's history and structure. In different universes or at different stages of our universe's existence, time might behave entirely differently. The boundaries of the universe, past and future, seem to be places where time itself becomes problematic. At the Big Bang, time did not exist before. At heat death, time may effectively cease to have meaning. These boundaries mark the limits of time, places where the arrow of time becomes abstract and the very concept of duration becomes suspect. Yet time is also intimately bound up with human consciousness, with the experience of existence itself. While physics reveals that time is relative, emergent, and perhaps illusory at fundamental scales, neuroscience reveals that the human brain's perception of time is constructed, malleable, and deeply dependent on attention, emotion, and neural processes. The subjective experience of time, the sensation that moments pass, that duration elapses, that the present is distinct from the past, and future arises from neural processes in the brain. Different parts of the brain process time at different scales. The cerebellum processes timing in the millisecond range, crucial for motor coordination. The prefrontal cortex processes longer durations. The insular cortex appears to be central to the sense of time passing. Remarkably, the brain does not appear to have a dedicated time receptor or a single time center, the way it has visual and auditory cortices. Instead, time perception seems to emerge from neural activity distributed across many regions. The brain constructs its sense of time from patterns of neural firing, from memory formation and retrieval, from the rate of incoming sensory information. And this constructed sense of time is surprisingly flexible. When attention is focused on a task, time seems to fly. Minutes feel like seconds. When waiting for something to happen, time drags. Seconds feel like minutes. Emergency situations, where attention is heightened and sensory information floods the brain, create the sensation that time slows down. Skydivers report that the minutes they spend falling feel stretched, expanded, almost in slow motion. These are not optical illusions, but real alterations in how the brain constructs temporal experience. Under stress, the brain accelerates its internal timekeeping. More sensory information is processed per unit of clock time, creating the illusion that external time has slowed. Psychoactive drugs that alter neural function can dramatically alter time perception. Time can feel to speed up or slow down, to lose its continuity, to become almost meaningless. These effects reveal that time consciousness is not a direct perception of an objective feature of reality, but rather a constructed neural representation. Memory is intimately connected to time perception. The subjective duration of events is influenced by the number and distinctness of memories formed during those events. Complex experiences with many novel elements are perceived as lasting longer than simple, monotonous experiences, even if they objectively occupy the same duration. Conversely, the more distant an event in memory, the more compressed it seems in retrospect. The philosopher's concept of specious present, the duration of subjective now, appears to be roughly 1 to 3 seconds according to neuroscientific studies. Events within this window are perceived as simultaneous, as parts of a single moment. The brain integrates sensory information across this window to create the impression of a continuous present. Yet this specious present varies. For people with certain neurological conditions, the present can seem much briefer or much longer. Attention influences it. Dopamine, the neurotransmitter associated with reward and motivation, influences the perceived speed of time. Even the sense of causality, the sense that one event causes another, is a construction of the brain, not a direct perception. The brain infers causality from the temporal sequence of events, from the proximity of events in space and time. If event A reliably precedes event B, the brain infers that A causes B, even if no actual causal mechanism connects them. The arrow of time, the sense that time flows from past to future, not the reverse, emerges from memory and causality. We remember the past, but not the future. We perceive ourselves as causing effects in the future, not the past. These asymmetries, which create the psychological arrow of time, arise from how the brain stores information, processes causality, and constructs experience. Interestingly, at the level of brain neurotransmitters and neural circuits, the equations governing neural dynamics are often time reversible. They do not inherently distinguish future from past. The arrow of time emerges from the brain's organization, its memory systems, its integration of sensory information, all processes that are inherently asymmetric. This parallels what physicists have discovered about time in general. The fundamental laws may be time reversible or symmetric, with the arrow of time emerging only at large scales from complex systems with many constituents. The subjective sense that time is passing, that moments flow from past to future, that the present is special and distinct, these might all be aspects of how the brain constructs a useful model of reality for survival and action. Just as the brain constructs a visual representation of space that is not identical to objective physical space, the brain constructs a temporal representation that is not identical to objective physical time. This suggests a profound possibility: time consciousness. The subjective experience of time as fundamental to awareness might be a neural construct as much as an objective feature of reality. The self, experiencing time, might be emergent from neural processes in the same way that space-time is emergent from quantum. Information or time is emergent from complex systems in thermodynamics. The physicist's abstract findings about time being relative, emergent, and perhaps illusory at fundamental scales align with the neuroscientist's discoveries that time consciousness is constructed and malleable at the level of human perception. Both reveal time to be less fundamental, less objective, less absolute than intuition suggests. In recent decades, physicists exploring quantum gravity, thermodynamics, and quantum information have proposed increasingly radical theories about time's nature. These theories suggest that time is not fundamental but emergent, a collective phenomenon arising from more basic quantum structures. The holographic principle, which proposes that three-dimensional space emerges from two-dimensional quantum information, implies that time is similarly emergent. If space is not fundamental but derived from quantum correlations, then time as part of space-time must likewise be emergent. Leonard Susskind proposed that quantum complexity might provide a deeper description of time than classical physics. In quantum systems, complexity roughly, the difficulty of describing the quantum state grows over time. Perhaps time's flow is literally the growth of this complexity. In this view, time is not a dimension but a measure of how complex the universe's quantum state has become. The physicist Juan Maldacena, who discovered the ADS CFT correspondence connecting gravity to quantum information, has explored connections between time, entanglement, and causality. In the holographic framework, causality in the bulk spacetime emerges from entanglement structure on the boundary. This suggests that the causal structure which events can influence which others and therefore the temporal ordering of events emerges from quantum information. Recent work by theorists like Mark van Ramsdonk on entanglement and spacetime geometry suggests that spacetime is not a pre-existing background, but is constructed from patterns of quantum entanglement. If spacetime emerges from entanglement, and time is part of spacetime, then time emerges from entanglement. In this framework, time's arrow, the asymmetry between past and future, might emerge from the growth of entanglement as quantum systems evolve. The past corresponds to states of lower entanglement. The future corresponds to states of higher entanglement. Time flows in the direction of increasing entanglement entropy. Other approaches to quantum gravity offer different perspectives. In loop quantum gravity, spacetime is quantized into discrete atoms of space, each with finite volume. Time in this framework would also be discrete, occurring in quantum jumps rather than continuous flow. In causal set theory, spacetime is fundamentally a discrete poset, a partially ordered set of events. The causal order determines the temporal sequence of events. Time does not exist independently, but is derived from the causal structure. These diverse theories, despite their technical differences, converge on a common theme. Time is not fundamental. Time emerges. The question is, from what does it emerge? The most compelling candidate is quantum information and the correlations between quantum degrees of freedom. As the universe evolves according to the Schrödinger equation, the quantum state becomes more entangled, more complex. This growth in complexity, in information structure, might be what we experience and measure as the passage of time. If this is true, then time is temporary and contingent. In different phases of the universe, where the quantum information structure is organized differently, time might flow differently. In the remote future, as the universe approaches maximum entropy and information structures dissipate, time might slow, stop, or lose meaning. The beginning of time at the Big Bang makes sense in this framework. The Big Bang represents the emergence of space-time and time from a quantum state. Prior to the Big Bang, time did not exist because the quantum information structure that generates time had not yet formed. The Big Bang is not an event in time. It is the creation of time itself. Similarly, the end of time at cosmological heat death makes sense. As the universe reaches maximum entropy, as the information structure becomes featureless and simple, time would effectively freeze. There would be no more growth of complexity, no more passage. These theories remain speculative and unproven. They exist at the frontier of theoretical physics, where imagination and mathematics meld. Yet they offer a profound reframing of time's nature. Time might be to the universe what temperature is to a gas. Temperature is not fundamental. It emerges from the collective motion of molecules. Remove temperature from a gas, and you simply have molecules moving. Similarly, time might emerge from quantum information dynamics. Remove time, and you have quantum correlations evolving according to unitary equations. The universe at its deepest level might be fundamentally atemporal, governed by timeless laws. Time emerges as a useful description when quantum systems become large and complex enough that the underlying entanglement structure can be approximated by classical spacetime. From this perspective, the universe does not exist in time. Rather, time exists and the universe emerges from it, as one of its emergent structures, no more fundamental than temperature or pressure. These radical ideas about time's emergent nature are not merely philosophical speculation. They make specific predictions that can be tested with increasingly sophisticated experiments. If time emerges from quantum information, then in systems where quantum coherence breaks down, where information becomes scrambled and inaccessible, time should behave differently. Experiments with quantum systems that preserve coherence versus those that decohere could reveal differences in how time flows or is perceived. If time is emergent from quantum gravity effects at the Planck scale, then experiments probing the smallest scales and shortest durations might reveal deviations from classical time behavior. Quantum gravity phenomenology searches for such signals in high-energy cosmic rays, gravitational wave measurements, and other exotic phenomena. Black hole observations provide natural laboratories. If time emerges from quantum information, then at the event horizon where quantum effects and gravity merge, time should behave in ways predicted by quantum gravity theories. Future observations of black hole shadows, merger events, and Hawking radiation could test these predictions. Atomic clocks have revealed gravitational time dilation precisely. Future generations of even more accurate clocks might detect subtle quantum gravity effects on time. Precision measurements of time at different altitudes, in different gravitational fields, or in quantum systems might reveal signatures of time's emergent nature. Yet beyond experimental tests lie philosophical implications that challenge human understanding. If time is emergent, then perhaps consciousness, which seems intimately bound up with the experience of time, is also emergent in a deeper sense. Consciousness, the mysterious phenomenon of subjective experience, always involves experiencing time, remembering the past, anticipating the future, existing in a present moment. If time is a construction of quantum information, and if consciousness emerges from quantum processes in the brain, then consciousness might be deeply connected to time's emergence. Conscious experience of time passage might reflect the quantum information dynamics occurring in neural tissue. This aligns with discoveries in neuroscience that time perception is constructed, not directly perceived, and is generated by neural processes that are themselves quantum in character. The physicist Penrose has proposed that quantum processes in neural microtubules give rise to consciousness. If true, then consciousness and time perception would be intimately connected to quantum information processing at neuronal scales. These ideas suggest that consciousness itself might be emergent from quantum information dynamics, just as time is. The sense of self, the experience of agency, the feeling that one is a unified entity persisting through time, all might emerge from the brain's construction of a temporal narrative from quantum information patterns. The implications extend to questions of free will and determinism. If time is emergent and not fundamental, if the future is not fixed in some higher dimensional space-time block, but emerges from quantum information dynamics, then perhaps there is room for genuine novelty, for true openness of the future. Classical physics suggested a deterministic universe where the future is completely determined by the past. Quantum mechanics introduced indeterminacy, but if time itself is emergent, then the very distinction between past and future becomes less absolute. The block universe picture, where all of space-time exists eternally and time's flow is an illusion, becomes more subtle when space-time is emergent. If space-time is constructed from quantum information, then it might not exist in a frozen, eternal form, but might be dynamically generated as quantum systems evolve. These philosophical implications reach toward questions that lie beyond current physics. What is the nature of existence? What is the relationship between consciousness and the physical world? Is the future truly open, or is it determined by the past? Physics cannot fully answer these questions, but insights about time's nature illuminate them. If time is emergent and consciousness is connected to time's emergence, then mind and matter might be less fundamentally distinct than classical philosophy suggested. Both might be aspects of quantum information processing at different scales. The question, can time truly stop, thus leads to deeper questions. What is time? What is existence without time? What would consciousness be if time did not exist? These are not merely scientific questions, but profound philosophical mysteries that touch the core of human understanding. The journey through the nature of time reveals a reality far more subtle and strange than everyday intuition suggests. Time is not what it seems. To an outside observer watching an object fall toward a black hole's event horizon, time literally stops. The falling object appears frozen, its clock ceasing to tick, suspended at the abyss forever. Yet the object itself experiences time flowing normally, crossing the horizon in finite proper time. At the speed of light, time dilation becomes infinite. From the perspective of a photon, though such a perspective is not physically valid, the entire journey of light across the cosmos occurs instantaneously. Time freezes at the fundamental speed limit. In quantum systems, time ceases to have definite meaning. The wave function evolves according to a time-reversible equation. Entanglement creates correlations that seem to transcend temporal ordering. In quantum gravity, time may not exist at all at the fundamental level. At the Big Bang, time itself began. Before the Big Bang, before has no meaning because time did not exist. And in the infinite future of cosmic heat death, time may effectively end, becoming meaningless in a universe of maximum entropy and equilibrium. The human brain constructs time from neural activity, from memory and attention, and the rate of information processing. The subjective sense of time passing is a neural construct, as malleable and contingent as any other sensation. And at the frontiers of theoretical physics, time emerges from quantum information, from the growth of quantum complexity, from the structure of entanglement. Time is not fundamental but derivative, not absolute but relative, not permanent but contingent. Can time truly stop? The answer is yes, it already does, in multiple senses. Time stops for light traveling at light speed. Time stops at black hole horizons from the perspective of distant observers. Time stops when entropy reaches maximum in a universe at heat death. Time stops in every quantum system, where the fundamental equations are time-reversible and indifferent to temporal direction. Yet from the perspective of observers embedded in these systems, time continues. The object falling into a black hole experiences time flowing. A spaceship near light speed experiences time passing normally. Quantum systems evolve through well-defined temporal sequences from the viewpoint of observers making measurements. This paradox that time both stops and continues depending on perspective is not a contradiction but a revelation. It shows that time is not a simple, objective feature of reality, independent of observers and reference frames. Time is woven into space-time in a way that makes it relative, perspectival, context-dependent. Moreover, the investigation of whether time can stop has revealed that time itself might not be fundamental. Time may be a convenient fiction, an emergent phenomenon arising from more basic quantum structures, no more fundamental than temperature or pressure. If time is emergent, then the question, can time stop, takes on deeper meaning. It is not asking whether the flow of time can cease, though that is true in certain circumstances. It is asking whether the emergence of time can halt, and the answer is yes. In systems where quantum coherence is destroyed, where information becomes maximally scrambled, where entanglement ceases to grow, time's emergence might pause or stop. The practical implications of this understanding are profound. If time is emergent from quantum information, then manipulating quantum information might offer new ways of understanding, and even potentially manipulating time. Technologies, based on quantum computing and quantum information processing, might allow unprecedented control over temporal phenomena. Not time travel in the science fiction sense, but manipulation of the quantum information structures from which time emerges. The human brain itself might be understood as a quantum information processor, constructing time from neural patterns. Understanding this might lead to new treatments for temporal disorders, new insights into consciousness, new ways of enhancing or altering temporal perception. Beyond technology lie philosophical implications. If time is emergent and consciousness is bound to time's emergence, then consciousness is not something separate from the physical world, but intimately connected to physical processes at the quantum level. The ancient philosophical problem of how consciousness arises from matter might find new illumination through understanding time's emergence. Mind might be as much an emergent phenomenon as time, arising from quantum information dynamics that create both temporal flow and subjective experience. The question, can time truly stop, is ultimately a question about the nature of reality itself. The answer that time is relative, emergent, perspective-dependent, and perhaps illusory at fundamental scales, revolutionizes understanding. Time is revealed as neither eternal nor absolute but contingent, temporary, constructed. Time is an accident of the particular quantum state in which the universe found itself at the Big Bang. In other universes with different initial conditions, time might behave entirely differently. This perspective is both humbling and liberating. Humbling because it reveals time, that most basic and seemingly eternal aspect of existence, to be temporary and derivative. Liberating because it suggests that time is not a prison or a fundamental constraint, but a feature of how the universe organizes information. The ancient philosophers pondered the nature of time and could arrive at no definite conclusion. Augustine asked, "What is time?" and confessed that he knew only when not asked. Newton assumed time was absolute and universal. Einstein revealed time to be relative. Modern physics reveals time to be emergent, perhaps even illusory in some sense. Yet time remains real within the domain of its emergence, the classical world where humans experience it, where consciousness flows with it, where life and death mark its passage. Can time truly stop? Yes and no. Yes, at the fundamental level where space-time emerges from quantum information, time's emergence can cease, and time can freeze from external perspectives. No, for observers embedded in the emergent classical space-time where time exists, time's flow continues unimpeded. The answer depends on perspective, on scale, on whether one is asking about objective reality or subjective experience, about the deepest physics or human consciousness. What remains clear is that time is far stranger, far more subtle, far more wondrous than common sense suggests. Time can slow, bend, warp, and freeze. Time has an origin and may have an end. Time might not be fundamental at all, and in recognizing time's true nature, in understanding that the most basic measure of existence is itself constructed, emergent, temporary, humanity is forced to reconsider everything: the nature of consciousness, the structure of reality, the meaning of existence itself. Time is not what it seems, and in that revelation lies both mystery and profound meaning.